Hello, welcome to the last part of the continuous distributions. I'm going to be solely talking about exponential distribution in this lecture. And I'm going to try to connect the exponential distribution to Poisson distribution from which it is derived on a couple of examples. All right, so what is, first of all, exponential distribution? Exponential distribution is the distribution's distance between successive events of a Poisson process. So here, this important point is the distance. Actually, when we are talking, if we are talking about the continuous variable as time, then it's going to be the temporal distance. If we are talking about the spatial directions or dimensions, then it's going to be distance in meters, kilometers, centimeters. So we are going to have a Poisson process. Think about the number of calls to an office example, and let's say that this is time. We have, let's say, one call here, another call at this time, another call at this time, another call at this time. And if you take a certain t period of time, then you may ask the question, what's the probability of having a number of n calls during time t, and that number of n calls will be Poisson distributed. Exponential distribution is going to be concentrating on this process, but what it asks, or what is trying to find, is not the number of calls, but the distance between two calls. So let's try to derive this exponential distribution. Actually, the derivation is pretty much informative. That's why I'm going to go over it. So basically, let's think that this is the continuum. It may be time, or it may be a spatial direction. It doesn't matter. It's the continuum on which Poisson process is acting or is happening. So this is one event, and this is another event. And during this interval, there is no events. There is no event happening. Therefore, this is going to be the distance between two successive events. And this is going to be the random variable for which we are going to derive the distribution. So we are going to define the define a Poisson random variable, but instead of calling the Poisson random variable x, we are going to call it n. Because the reason is we are going to reserve the name at the title x to the distance between two calls. Anyway, the Poisson distribution is simply equal to this. Basically, here there is nothing new under the sun. It is just that I have replaced n here with x. So in the previous, that may cause a confusion for those who remember the previous notation for Poisson distribution. For previous notation for Poisson distribution, we use this. Here, x denoted the number of calls, and t was the time segment we were interested in. And the number of calls was the random variable. Here the roles are changed. I just replaced t and x. I just changed x by n. So the number of calls in this case is going to be equal to exponential number lambda times x, and x is the time interval I'm interested in. It's not defined yet. So this is going to be again lambda x. Therefore, I'm concentrating on a region of length x, and then the expected number of calls during that interval is going to be lambda times x. So this is going to be to the power n factorial. So actually it's the same expression, but only x and n change. Okay, so I'm going to continue with this. Let me get rid of these. I'm going to continue from this point, actually this scheme that I presented here. During this x, note that since this is distance between two events, between two successive events, since we say successive, maybe we should have added here successive. Since these are two successive events, therefore it means that there is no event happening during this x. Therefore, n is equal to 0. So we are searching for the probability that n is equal to 0 during this x. And note that, well, actually, if you just put n equals 0 here, this is going to be equal to 1, this is going to be equal to 1, and we just end up with exponential minus lambda x. But more than that, or actually maybe a little bit much more difficult to see, this is going to be equal to probability of capital X smaller than this lowercase x. What do I mean by that? Since there is no event happening during this x, small x, the next event is going to be sometime distant from this previous event, much more than that x value. Therefore, what we have found here is that probabilities n is equal to 0 is equivalent to saying probability of the next event is going to be at least for a time interval of x, lowercase x. So the next event is going to take place after a time distance of x intervals. I don't know whether this was clear enough, but I hope you get the idea. Well, up to this point, it's just arithmetics. It's pretty much straightforward. But jumping to this part needs a little bit of thinking. Once you understand this, actually what we have is this one. We have a random variable x, which is greater than some x value. The probability is going to be equal to exponential lambda x. Now what we do is we find fxx here, which is going to be equal to 1 minus probability of x greater than 0, which is going to be probability x smaller than x. And this is going to be simply equal to 1 minus exponential lambda x. Now we go back to the basics. Remember the definition that if our cumulative distribution function is continuous, differentiable, then when you take the you differentiate it with respect to x, you obtain the probability mass function. And that's what we do here. We just take the derivative with respect to x. So if you do that, it's going to be 1 minus exponential lambda x over dx. We are going to end up with lambda exponential minus x. And this is going to be the probability density function of x. And what was x? X is the distance between two successive events. That's exactly what we were trying to achieve. So this is the probability mass function of an exponential distributed random variable, distance between two successive events in a Poisson process. And when you find, well, this is a probability mass function. Well, this one is also pretty much handy. We are going to be using this property in many questions. Probability that x is greater than some lowercase x value is going to be found by this expression. Of course, you can find this value by integrating this value from x to infinity. Note that, let's put it that way, probability of x greater than x is going to be equal to that we are going to x to infinity lambda exponential lambda x. But note that when you do this integration, you are going to find this result. So it's pretty much practical to keep that result in memory. So once we find the probability mass function, the next thing, or probability density function, what we do next is find the expected value and the variance. You can find these values using the usual expectation operator formulation. So x times lambda exponential lambda x dx. From note that the domain of x is going to be from 0 to plus infinity. Actually, this is important here. I should have mentioned that here. The domain of x here is let's put it that way. The domain of x is going to be, I think I should not include a 0 here, because at the same time, two events cannot occur. So x is going to be a real positive, real number. So it's a continuous number. Anyway, so let's go back here. So the integration is going to be from 0 to infinity. It's going to be this one. Well, actually, you need integration parts to compute this integration, because you have x and exponential minus x. So I'm just going to omit the results. So what we obtain here is 1 over lambda is expected value, and 1 over lambda square is going to be the variance if you follow the same procedure. So just like geometric distribution, exponential distribution is also have that lack of memory property. Actually, for those who have watched the bonus video, I prepared a bonus video related with this part. As for those who have watched it, it's going to be easier to follow here. So lack of memory property in mathematical terms is going to be equal to x, the distance between two events, greater than some t1 value. Given this condition, we ask what is the probability that x is smaller or greater than, it doesn't matter, greater than t1 plus t2. Now, once that T1 has passed, the process has got no memory. It is as if starting from a process with T2, which is from 0 to T2. So it's like this. So let's say we are here, T1 plus T2. Let's say we have no call up to this point. So X is going to be greater than T1. What's the probability of having a call at that time? Smaller than T1 plus T2. It is as if this process has now started from this point. This origin has shifted here. Therefore, we are going to be only interested in this distance, additional distance T2 here. So once, if you find this probability of X2 smaller than T2, you are going to be answering this question. Well, the proof is going to be very simple, especially for those who have watched that bonus video. We just write that conditional probability here as the intersection of two events. Note that conditional probability x greater than t1 and intersection of x smaller than t1 and t2. Note that this means that x is greater than t1, x is smaller than t1, t2. So we can write it in this manner. So basically, the numerator is going to consist of this term, whereas the denominator is going to be consisting of, due to the definition of conditional expectation, is going to be equal to probability of x greater than t1. So what we do here, we just, in the integral relating to exponential distribution, you just put, actually, if you integrate from t1 to t2, and if you divide this from t1 to infinity lambda exponential lambda x dx, you are going to find the same result. But actually, there's even a practical method. Note that this is going to be equal to probability of x greater than t1, which is a larger set, and a probability of x1 greater than t1 and t2, because if this is our time axis, and this is t1 and t1 plus t2, probability of x1 greater than t1 corresponds to this region. So it has a higher probability corresponding to the second probability. So if you subtract those two, the exclusion of that second part will correspond to the region which is between t1 and t1 plus 2, which is the region that we would like. And note that in the previous slide, I have already shown you that probability of x greater than x can be directly, this result can be directly used, which is actually nothing but obtained from the integral. So this is going to be exponential minus t1, and this is going to be equal to exponential minus t1 plus t2 over exponential minus t1. This is going to be, if you cannot see very clearly. So if you do the arithmetics, the common factor here, exponential minus lambda t1, is going to cancel out, and we are going to be obtaining this result. And basically, this is exactly equal to cumulative distribution value of t2, which is going to be equal to probability x smaller than t2, which is finalizes the proof. So basically, history is not important. Just like geometric distribution, what only matters is the current distance. This is the moral of the story. All right, I'm going to be solving two questions, but they are going to consist of many parts. Let's start with those questions, and there are going to be some a couple of intricate parts or some details which you should pay attention. Time between calls is exponentially distributed. Since the number of calls is Poisson distributed usually, this shouldn't come like a surprise, with a mean time between calls equal to 15 minutes. So mean time between calls is given. Let's see. A, number of calls within a 30-minute interval. What is the probability of, no calls within a 30-minute interval? So let's start. Again, like all questions, we start by defining the random variable. X is going to be equal to time between successive calls. Please note that you should start using this approach. Now, X is exponential distributed. Do we know its parameter lambda yet? No. What we know here is the expected value of X. Expected value of X is given as 15 minutes. Now, if we go back here, you should see that the expected value of exponential random variable is 1 over lambda. And this is the very same lambda rate of the process that we have seen in Poisson distribution. So this is going to be equal to 1 over lambda. Therefore, lambda is going to be equal to 1 over 15 minute to the power minus 1. Now we have also the rate of the process. So the question simply asks, what is the probability that X is going to be greater than 30 minutes? Note that this corresponds to no calls within 30 minutes. You can actually solve this question using Poisson distribution here, but just by using exponential distribution, note that this is going to be equal to lambda times 30, because X is going to be equal to 30. So it's going to be equal to 30, 50, and this is going to be equal to, I guess that is the case. Yes. So here lambda is equal to 1 over 15. So this is the answer. Now, probability of at least one call within 10 minutes. Now, this at least is actually, you are going to realize that that additional word at least or exactly one call is going to make a difference. Now, at least one call question can be easily answered using probability of the time between two successive calls is smaller than 10 minutes. Now, first of all, let's realize why this corresponds to this very simple condition correspond to at least condition. This says that the distance between two calls is less than 10 minutes. For instance, it allows the possibility of such an occurrence. Let's say this is time 0. The next call is here at minute 4. And there is an additional call here at 9 minutes. This is included in probability X is smaller than 10, because actually what it's only searched for is this X value. This also allows the possibility of something like this, 999. There is a minute. There is a call here. And the next call is maybe 1,000 years later. It doesn't care about. But what it only cares about is the next call. Therefore, if this condition is satisfied, that at least condition would have been satisfied. But note that this is not equal to, if we just erase this part, exactly if we say one call within 10 minutes, condition does not correspond to that condition. That's the very important thing. So exponential distribution is the distance to the next call. That's the important point. So this is going to be simply equal to, well, if you like, you can write it into integral form, or you can use this very simple formulation. This is going to be from 0 to 10 lambda exponential lambda x dx. So it's going to be from 0 to 10 lambda value 1 over 15 exponential x over 15 dx. And actually, if you practically solve this, note that x greater than some value is this one. So 1 minus this value is going to be the correspond to the cumulative distribution function. So this is going to be equal to exponential minus lambda x, which is going to be equal to 1 minus 10 over 15, I'm sorry. And this is going to be equal to 0.487. So there's something like a 50% probability. And it makes pretty much sense because we have a 15-minute expected value of calls between, we have between two calls. So at least one call within 10 minutes, it's pretty much acceptable that is the value that we obtain. Now, let's continue the next call between 5 and 12 minutes. For this question, I'm going to be using two methods. First one, is probably, this is the method that probably is going to seem easier to you, but try to understand the second one also, because the second one is going to be much more informative in handling and understanding the exponential distribution, and for finding results for other questions also. So it says the first call between 5 and 12. Well, probably what you would do is, okay, so this is actually what the question asks. So let me not write here the first method yet. Let me write here the first method. The first method hasn't started. So this is actually what the question asks. Actually, one thing that you may do is, probably what you think of, is solve this integral, and this is correct. But let's see why this is correct. It's not that much straightforward, because the definition of exponential distribution is a little bit tricky, as I said. This is, I'm sorry, x15 dx is going to be, I'm just going to copy from my notes. This integral is going to be 12/15, and the result is 0.267. Okay. Now, this is a correct result. However, it depended on the kind of the type of question that is being asked. If the question were any call between 5 and 12 minutes, which means, now when it says the first call, it means that there is no call from 0 to 5 minutes. Here, actually, when you take the integral, there is that hidden that information, or that condition is actually hidden here. Because note that what this corresponds to here, x corresponds to the time or the distance until the successive next event. So when it says the first call, yes, this is satisfied, because the next event doesn't occur up until the 5th minute. Therefore, this integral is valid. But if the question asked, I don't care about the first 5 minutes, there may be a call, but there should be a call between 5 and 12 minutes, that wouldn't be the answer. That may seem tricky, but as I said, the important point here is to understand the meaning of this x and the corresponding integral. This integral again suggests that there is no event in the first 5 minutes, and there is going to be at least one event during 5 to 12 minutes. So it means the first call. And please note that this condition also says that there may be more than one calls between 5 and 12. So all of these conditions are buried inside this integral. The second method actually makes this much more clear. The second method actually here, now this is going to be equal to probability that no calls in the first 5 minutes. So I'm going to write everything clearly and try to come up with the answer. And this is going to be multiplied by what? How can I multiply with the second condition? I'm going to explain it in a minute. At least one call within the next 7 minutes. Now I can multiply these, because here, think about this, 5 minutes and 12 minutes. Now in Poisson distribution, what occurs here is independent of the occurrence of here. Actually, if you think about the derivation of Poisson distribution for every very small time interval of delta t, all of these trials are independent from each other. Therefore, these time segments are also independent from each other. Therefore, since we have 2 independent time segments and 2 independent events, we can multiply the probabilities. Now, probability of no calls in the first minute means x is x is greater than 5 minutes. Now the second condition is going to be probability of, well, if you like, we can write it that way, smaller than 12, x greater than 5. And note that this is going to be, due to lack of memory property, is going to be equal to probability of x smaller than 7 minutes. So therefore, what we have here, probability x smaller than 5 minutes multiplied by probability of x smaller than 7 minutes. So I repeat again, this means in the first 5 minutes, there is no event. And in the succeeding 7 minutes, there is at least one event. This corresponds to the first call. This actually, these two conditions overall correspond to the first call. And I repeat again, this second condition also comprises more than first calls. If the question were the first and only one call between 5 and 12, we should have done something else. Anyway, now comes solution of the problem. The first one, probability of x smaller than 5 minutes is going to be 1 minus exponent. I'm sorry, this should be greater than 5. I'm very, very sorry for that. All right. X greater than I have written everywhere, but this was so because there is no event in the 5 minutes, and in the second 7 minutes there is one event. So this one is going to be equal to exponential minus lambda times 5, and this is going to be 1 exponential lambda 7. So if we write the whole thing, it's going to be exponential minus 5 over 15 times exponential minus 7 over 15. And if you do the calculation, the very same result is obtained. As I said, this second method maybe seems a little bit complicated, but you should understand this method because the solving using this integral is going to be valid only for a small number of questions, as I said. This method with only using this integration between two limits is going to correspond to a single type of question. You don't have that much flexibility. All right. I should get rid of these. Find the length of time such that probability of at least one call in the interval is 0.19. So that's a different question. It asks, okay, that was the last call. Let's put the origin here. So this time goes like this. So we should, what is going to be the value of time? For instance, t is going to be at that value such that probability of at least one call here is going to be equal to 0.90. So in these type of questions, it's important to understand a special rate with exponential distribution, what is going on and how can I convert it to mathematical terms. It means probability of x. X is the random variable that I'm interested in. And let's call this length of time, actually call it time to make it easier to understand. And so this is going to be equal to also time. All right. Oh, by the way, we call this x. X is smaller than a certain value of time, which we do not know yet. This value is going to be equal to 0.90. Now, does this condition correspond to what is asked in the question? Let's first check that. Yes, because actually this means that since it says at least, it may be anywhere here. This actually includes the possibility that time was at that point, right? The first call, but that's okay because I'm only interested at least condition. So it may be anywhere here, but not more than this time value. So actually we are searching for this time value here, which satisfies the 0.90 probability. So therefore this time, this is going to be represented by exponential minus time divided by, or let's write it first like this, lambda times time, and this is going to be 1 minus lambda time divided by 15, which is equal to 0.90. So if you do the maths, it's going to be equal to 0.1 is equal to exponential minus time over 15. If you take the logarithm of both sides, it's going to be a logarithm 0.1, or let's call it ln. ln 0.1 is going to be minus time over 15, and time is going to be found at the end as 34.5 minutes. Okay, the second question I'm going to be solving is going to is aimed to demonstrate the relation with exponential and Poisson distribution more clearly. So what it says is we are talking about an airport and time arrival between between planes on an airport is exponentially distributed with a mean of 1 hour. Here I should have said 1 hour. So time arrival, it means we have our airport. Well, it should be this. And so we have a plane here, and another one is here, and actually this one lands, and the time between two, let's call it t or x, we are going to probably call it, the time between the arrival of two planes is Poisson distributed. I'm sorry, exponential distributed. Let's see what the question asks and then continue with the question. What's the probability of more than 3 aircrafts arrive within 1 hour? First of all, before even understanding what the question is, I define my random variable x. Since this is going to be about the time arrivals or time between arrivals, I'm going to be concentrating on the exponential distribution. So I'm going to define x as time between successive arrivals of planes. All right, so x is exponential distributed. What we only need is the lambda rate parameter. Do we know it? Not directly, but we can easily find it. Expected value of x is equal to 1 over lambda, and this is given as 1 hour in the question. Therefore, lambda is equal to 1 hour to the power minus 1. That's great. Now, the question, more than 3 aircrafts arrive within 1 hour. It says more than 3 aircrafts. Now, this doesn't seem like a very easy question to be solved with exponential distribution. Actually, there is a distribution called Erlang distribution, but we are not going to talk about that. So can we solve this using some other distribution? Yes, we can, because every question that can be solved by exponential distribution can also be solved by using Poisson distribution. Therefore, I define my second random variable. This is number of planes which arrive within 1 hour. Note that I do not call this again x, because then otherwise it's going to be confusing. So therefore, probability of n equals n in this case is going to be equal to exponential minus lambda to the power n and n factorial. Well, since I call this 1 hour, this is lambda times 1, lambda times 1. So I didn't write this. So, and this is going to be, n is going to be equal to 0, 1, 2, to plus infinity. So here n is going to be Poisson distributed. So what the question asks is basically, what is the probability that n is greater than 3, more than 3 aircrafts within 1 hour? Therefore, this is going to be basically equal to 1 minus f, and I write here because I have two random variables, I write the probability density function, probability mass function subscript here. This is going to be 0 minus fn, 1 minus fn, 2 minus fn, 3. So therefore, I'm going to be writing all these values. It's going to be exponential to this, since lambda is equal to here. Where is my lambda? Is equal to 1. This is going to be exponential minus 1. And here I'm going to be writing all these values one by one. This is going to be equal to 1 plus 1. When it comes to actual, this is, I have written this one also. When it comes to this, it's going to be 2 to the 1 to the power 2 over 2. So it's going to be 2. And the last one is going to be, this is always going to be 1 because lambda is equal to 1. It's going to be equal to 3 factorial. So basically, it's going to be equal to 6. So if you do the computation, it's going to be equal to 0.019. This is the probability that there are going to be 3 aircrafts arrive within 1 hour. And let's check whether this makes sense, since it is expected for 1 airplane to arrive within 1 hour. 3 airplanes is a pretty much large number. So therefore, it seems at least plausible that the probability is pretty much low. Okay, if 30 separate 1 hour intervals are chosen. So I have only talked about a 1 hour interval. Now the question may be which 1 hour interval, from 0 to 1 hour or 1 to 2. It doesn't matter, because exponential distribution, and the previous question was basically about exponential distribution, it has a lack of memory property, so any 1 hour interval would have been sufficient. You can randomly choose the origin at any point. So using the same logic, if we separately, without overlapping, note that these should be independent, it can be like this. Of course, it should be 1 hour, so at least the width should be identical. So think about equal width segments, and this is on my time axis here, right? Non-overlapping 1 hour intervals are taken. Any way that you lose, that you like, it doesn't matter. As long as they do not overlap, therefore they're going to be independent, it's going to work. If 30 of these, 1, 2, 3, 30 of these are chosen, then what's the probability that no interval contains more than 3 arrivals? Note that in the previous question, I have found that the probability of 3 arrivals, probability of more than 3 arrivals, is equal to 0.014 for a segment, for one segment. That was the result I have found previously. Actually, let's call this P. Let's call this even success probability. So within that time interval, there are 3 planes. There are more than 3 planes, I'm sorry. At least 4 or 5 or more planes coming to the airport is this one. And what the question asks is, none of the intervals satisfy this condition. Therefore, what we have here is actually a binomial random variable. You should realize that, because each of these trials will consist of one segment satisfying this condition or not. So basically now I'm going to be defining a new random variable x. This is going to be the total number of successes, and here this is how success is defined, out of 30 separate 1 hour segments. And when I say success, I mean more than 3 planes landing. So now x is, this is the, I think these 2 steps are the most important steps. Is binomial distributed with a number of trials 30 and a success probability 0.090. And what the question asks is, what is the probability of x is equal to 0? So actually, once you make these definitions, define x, define the distribution of x, and now convert the question into mathematical form. Now the rest of the question is straightforward, because we can easily find this as the distribution, which is going to be, I'm going to copy here, it's going to be equal to 0.563. All right, so the next question is that related with that tricky wording of first, at least, blah, blah, kind of thing. What is the probability that the first arrival is between 1 and 1.5 hours? So here is the idea. If you take any origin here, starting from 0, we have 1 hour here and we have 1.5 hour here. There is going to be no arrival here. The question suggests that, because it says the first one. And there is going to be at least 1 arrival here, because the first also suggests this one. There may be more than 1 here. I don't care. The first one should arrive anywhere in this segment. So basically, it's going to be, I'm going to again solve this using 2 methods. But first, again, let me define the random variable. X is going to be equal to time of the first arrival. And x is going to be exponential distributed. Now the first method is, note that this condition actually satisfies that the using of integral. So we are going to be asking the question 1 hour x smaller than 1.55 hours. So it's going to be from 1 to 1.5. We have exponential minus, what was lambda value? I think it was equal to 1 times x dx. So when you solve the whole thing, it's going to be exponential minus 1.5, and the result is this one. Straightforward. But actually note that this corresponds to no landing during first hour, because x should be, the next one should be only between 1 hour and 1.5 hour. All right, now the second method. The second method is going to be similar to what I've previously done. So it's going to, if you understood it, the previous question, that's going to be just a repetition. For those who have find it a little bit hazy, it's going to be, I hope it's going to clarify a couple of things. So this is going to be equal to also probability of x being greater than 1 hour times probability of x smaller than 1.5 hour given x greater than 1 hour. Actually, it says, this statement says that there is no event during the first 1 hour, and given that there is no event during the first hour, there is going to be an event during the next 1.5 hour. Now, due to lack of memory property, this can be written as probability of x smaller than 0.5 hour. So therefore, the result is going to be x greater 1 hour multiplied by probability of x smaller than 0.5 hour. Note that this may sound strange at first sight. Well, actually, how can be something more than 1 hour, and how can be something at the same time smaller than 0.5 hours? Think about it as two different segments, then it's going to work. So time of the first arrival is going to be, it's not going to satisfy both of these conditions within the same interval, but as I said, the second statement comes through the lack of memory property, so it actually it is used in another segment. So basically, the rest is going to be pretty much simple. This is going to be exponential to the power minus 1, because x greater than 1 hour, and the second condition is going to be 1 minus exponential minus 0.5. And if you do the arithmetics, the result is going to be again the same value. Actually, we are going to realize that this second method is going to be applicable, or is going to be more handy in the next question. The next question is, what's the probability that there is at least one arrival between 1 and, let me see this again, 1.5. Now note that this is different from the previous question. In the previous question, it says the first arrival is between 1 and 1.5. This actually implicitly means that there is no arrival within the first hour. This, on the other hand, says nothing about the first hour. It says, I don't care about the first hour. There is at least one arrival between 1 and 1.5 hours. That's sufficient for me. That's the very important thing. So again, defining x as time of arrival. Excuse me. First method here will be probability that x is smaller than, all right, it's going to be 1, oops, where did it go? Yeah, 1.5, given that x is greater than 1 hour. And therefore, this is going to be, due to lack of memory property, is going to be simply equal to 0.5. What the very important point is a distinction between this term and the previous one. Note that the very same term existed here. but we multiplied this term by another one, that additional condition that there is no event during the first hour. The first arrival statement actually necessitated putting this term here. In the second one, we don't have that necessity. We don't care about the first hour, so just what we only care about is that there is at least one arrival between first and the first 0.5 hour. So x is greater than 1, x is smaller than 0.5. This is the only condition that I'm interested in, right? So I don't care about the rest. Therefore, we just put the values here. This is going to be 1 minus exponential 0.5 and 9/4 is the result. And the second method is, as I said previously, you can always use Poisson distribution if you are not very comfortable with exponential distribution. As you can see, one needs to really think about the exponential distribution. This is going to be number of arrivals during a 0.5 hour period. In this case, n is going to be a Poisson random variable with lambda equal to 1 hour to the power minus 1 term. Lambda is equal to, with this parameter. So what we are asking here is probability of x smaller than 0.5 hours. We are interested in this quantity. It means that probability of this n is greater than 0. It means during this time there is at least one. It means it may be 1, 2, 3. As long as it's not equal to 0, we have during that 0.5 time interval, we have a non-zero number of arrivals. And this is going to be simply equal to probability of, or let's just write it that way, f n 0. So this is going to be equal to 1 minus exponential minus 1 times 0.5 if you write the Poisson distribution, and it's going to be equal to the same value. So note that, please, that would be a good exercise. Whichever question you solve using exponential distribution, try to also solve it using Poisson distribution. All right, so the last question that I would like to answer is, what's the probability of exactly one arrival between 1 hour and 1.5 hours? So note that part C, D, and E asks almost the same thing with small subtle differences, and these differences are important. In part C, it asks the first arrival in that interval. The part D asks at least one arrival, and part E asks exactly one arrival. Well, here actually when it says exactly, we cannot refer to exponential distribution. It's going to be Poisson distribution. Again, this is going to be number of arrivals during a 0.5 hour period we are talking about. And then it's going to be this 0.5 hour period that we are talking about. You may say, but this was between 1 and 1.5. Can we take it as any 0.5 interval? Yes, we can, because as I said earlier, Poisson distributed delta t's are independent. Therefore, this segment will be independent for over all of the previous segments. So you can easily take this as any 0.5 hour period. So we ask the probability of n is going to be exactly equal to 1. This is what is asked in the question. In the previous question, it was 1 minus n minus n is equal to 0, because it meant at least 1. But here it says exactly 1. Therefore, we just directly use the Poisson distribution formulation. This is going to be times 1. This is going to be 0.5 times 1 to the power 1 over 1 factorial, if I've done it correctly. And the result is going to be 0.333. Now note that this value is smaller than, let me write the value also here, 0.3033. So probability that n is equal to exactly 1 is 0.3033. This is smaller than this value. Why? Because we have only one landing here. On the other hand, this says at least one landing. Of course, this is going to compromise, or this is going to consist of 1, 2, 3, all up to infinite number of landings. Therefore, this value should be, of course, smaller than that value. If you also include 2, 3, 4, up to infinity, you are going to converge to this value. Okay, so that's all I'm going to talk about exponential distribution.